Hello and welcome to this film, which is about I suppose yet another type of spectrum, but it's very closely linked to the electromagnetic spectrum, which hopefully you've just watched a film about. So here we're going to be looking at atomic line spectra, and more specifically we're going to hopefully know what we mean by a line spectrum, and this could be one of two different kinds. It could be an absorption spectrum or an emission spectrum. And hopefully we'll also try and make some kind of connection between the existence of these spectra and the Bohr model of an atom, which, remember, well, you might not remember, but the Bohr model of the atom basically describes an atom as having electrons in different energy shells. Okay, and not only that, but hopefully we'll be able to start using these spectra to actually identify particular elements. Okay, so first of all, let's describe the difference between a line spectrum and a continuous spectrum. Now, we've seen a lot about continuous spectra in the film about the electromagnetic spectrum. Here is the continuous spectrum of visible light. When we say continuous, that means it kind of contains everything along the way. Okay? This is a line spectrum, and what you might see is that the colours line up precisely with the continuous spectrum, but there's lots of things missing. So these black areas show where there's no light in this spectrum. The bright areas are places where we are seeing light, but only in particular places or in lines that correspond to particular wavelengths. Okay? Now, it would be perfectly possible for us to have an absorption line spectrum, and that would look like a kind of negative photograph of this. So we'd have lots of large bright regions separating dark lines that would correspond to these wavelengths. Okay, but we'll have a look at that in a little bit more detail soon. I really just wanted to show you here what the difference between a line spectrum and a continuous spectrum is. Now, as I said before, we're going to try and relate the existence of these spectra to the idea that atoms have electrons in different energy shells. Okay? Now, the Bohr model of the atom, quite simply, for the time being, says that electrons can exist in different shells, and that the higher the number of the shell, the higher its energy will be. Now, an electron could find itself in a high energy shell, and then it could move to a lower energy shell. But it can't just do that without emitting some energy, because energy has to be conserved. So the idea is that electrons can move between these different energy levels in the Bohr model, but if they're going to do that, they're going to have to either absorb energy when they go up in energy, or they're going to have to release energy when they come back down. So what causes these lines in a spectrum? Well, to start understanding that, we're going to start introducing some key terms which almost sound like personality traits of electrons, but which are proper terms which we should understand the meanings of. So we've got excited electrons. Excited electrons are ones which find themselves in a higher energy shell than usual. When we talk about an atom's ground state, we're talking about this usual state. So in other words, where the electrons would be if they could be in the lowest possible energy shells. And normally when we write an electron configuration in chemistry, we're talking about this ground state. Okay? Now electrons that are excited could relax. So they could fall down from their excited states back into their ground states. So let's say I had an electron out here in the sixth shell, 1, 2, 3, 4, 5, 6. If that fell back down to the first shell, it would emit light of a particular energy, okay, because there's a difference in energy here. And in actual fact, the difference between the sixth shell and the first shell, this is an atom of hydrogen, is light with a wavelength of 94 nanometers. If you went from the fifth shell to the first shell, then the light would have a wavelength of 95 nanometers, which makes sense because the energy gap is smaller and therefore the wavelength should be longer. Okay? Now there's lots of different ways that electrons can fall back down into lower energy states. We don't need to know the different kinds, but just very briefly, we could, for example, have an electron falling from the sixth shell back down to the second shell. Okay? Or from the fifth back down to the second. And there could be lots of different transitions from high energy cells back to the second. And as it happens, when we measure those wavelengths, we're talking about the Bohr series in the hydrogen atom. But just to stress the point here that we're not concerned with what the names of these series are. Simply the fact that when an electron falls back down from an excited state to its ground state, it will emit energy. And likewise, if we take an electron from its ground state and excite it into an excited state, then it's going to absorb energy. Now, how on earth is that connected to a spectrum? Well, let's have a look here at what actually happens to be the Bohr series in the hydrogen atom. It takes place in the visible range of the electromagnetic spectrum. So here we've got red and here we've got violet radiation, gradually decreasing wavelengths or increasing frequencies. Okay, now let's have a look at what these transitions are. We've got one from the third shell back to the second. We've got one from the fourth to the second. We've got one from the fifth to the second, one from the sixth to the second. Okay, and there's others as well. In fact, there's an infinite number of different shells. But what you can see, hopefully, is that as you go higher and higher in number, the shells get closer and closer together in energy. Okay, so here at the highest energy out of these four transitions, because the biggest energy gap, at the highest energy is this line here. Okay, at the next highest energy is this line here. At the next highest energy below that is this line here, and notice there's a bigger gap between those two than there was between these two, because there's a bigger gap between these two shells than there was between those two shells. Okay, so we're starting to see in a little bit more detail how these lines that appear in this case, an emission spectrum, can correspond to different energy jumps of an electron from excited states back down, relaxing back down into a ground state. Now, here we're looking at the two different kinds of spectrum that I've just been talking about, an absorption spectrum and an emission spectrum. Now, these are both for hydrogen. You can see these are the same lines we've just been looking at. Now, you could potentially give hydrogen atoms lots of energy. This would promote their electrons into higher energy orbitals, and as they fell back down, they'd emit light. Okay, and that would give us this emission spectrum. On the other hand, you could shine light at hydrogen, and it could make those exact same electron transitions, but in reverse. So instead of emitting light as they fell back down to low energy levels, they could absorb light as they went up from those low energy levels into their excited states. Now, because the energy gaps would remain the same, we'd expect the lines to appear in exactly the same places, or exactly the same colours, or the same frequencies, or the same wavelengths. But the absorption spectrum, because it's created by electrons absorbing energy, is missing the light that they absorbed. An emission spectrum, which is a dark background, is just showing the light that is emitted by electrons as they fall back down from excited states. And this is basically the same slide, but we're now talking about the fact that spectra are like element fingerprints. This pattern of lines that I see here for hydrogen would be different to any other element. Okay, so it's almost like we can use these spectra as a kind of fingerprint to show us which elements there are in a sample. So one of the things that I suppose fairly early astronomers did was they looked up at the stars and measured the frequency of light that was coming to us from those stars, and used a knowledge of what the different fingerprints were for the different elements to see what elements there were in very, very distant galaxies. So if they observed this pattern here, where the light was coming to Earth and we could see all these different frequencies, except there were missing frequencies where the gases in the star's cloud were absorbing particular energies of light, we could go, oh, well, that star's got hydrogen in it. Okay, so because they're all different for different elements, we can use them to identify elements. Now, just before we kind of have a look back at what we were supposed to learn from this film, let's just make sure that we know what the key points were. Right? There's a difference in energy between the levels that can be occupied by electrons. That's what we kind of call these shells, right, in the Bohr model of the atom. Different frequencies of light correspond to different energies of light and different wavelengths. So the gaps in energy between these levels will also correspond to certain frequencies or wavelengths. Excited electrons, so that is ones that we've given energy to and have bumped up into excited states, will relax back down to their ground state sometimes they might relax to other energy levels, and as they do that, they will emit energy. The flip side of this is that if we excite electrons with light of all different frequencies, then they will only absorb certain frequencies. Okay? But here they'll be absorbing light as they get excited up into excited states rather than emitting light as they fall back down into ground states. Okay? Now, we call these different series of emissions different names, and they occur in different regions of the spectrum, but this point here, whilst I suppose it's relevant to what we've been talking about, is not something that you're going to be tested on. Okay? So, there you are. So hopefully now you understand what a line spectrum is. You know the difference between an emission spectrum and an absorption spectrum. In a moment we're going to be, in the next film, we're going to be looking at how we might use absorption spectroscopy to actually measure things in samples of substances. Okay, and to do that I suppose we're going to need to be aware of the fact that we can identify elements using these spectra. Hopefully it makes sense. If you've got any questions or comments, then please come and see me or post a comment on YouTube.